Hello, I'm Mr. McBrien, and this is TEJ3M, Circuit Schematics. Yesterday we talked about some of the definitions to do with circuits and to do with electricity. We talked about Ohm's law. Today we're going to talk about schematics. We're going to talk about communicating circuits in an accurate manner. Now I know we've already shown some pictures of these things, but what we'd like to do is to understand how to create our own schematics that match accepted processes, particularly in North America. So how do we make sure we communicate our designs accurately? Well, first off, we want to understand a bit about the motivations of this. When we design things, we rarely design a device, an invention, a widget. We rarely make the design with ourselves as the audience. Typically, we're going to be part of a team that activates this invention, that creates something. And text-based communication, paragraphs describing three-dimensional systems are just not effective. So we need pictures to be able to communicate our circuits. And in order to communicate in our most effective manner, we want to follow accepted practices. So, accurate schematics are extremely important. Even if we are a small organization, we may have to submit patent documents for a broader audience, the entire world. If we're a medium-sized organization, we'll be communicating with coworkers down the hall. If we're a larger organization, we may be communicating with coworkers around the world. And we want to see, when we're finished, accurate prototypes. We want to see that the thing that we conceived is the thing that God built. And a bad schematic will result in something being built that is not what was conceived. It can be inconvenient. It can cost weeks in terms of prototyping turnaround, or it can be dangerous. So our basic tools then to communicate schematics. Lines, of course, represent wires, as we've talked about before. Dots on the lines represent conductive joints. They represent solder, right? And it's important to note that intersections between lines are not necessarily connections unless it's the only option available. So there aren't any dots to speak of in this circuit representing solder, but we don't really need them because it's obvious that the lines are not intended to go off into nowhere and that this is a circuit, so we don't bother putting in our dots in the corners. So these, to be clear, these corners are connections between the wires. Now in contrast, this more complicated circuit has dots representing solder where there's a possibility that it's something else. Dots showing connections where there are multiple options. And it also has a place where the wires cross for convenience sake. And there's no dot. There's no connection here. This wire is crossing over the other one, but it's not connected up with it. In some cases, we'll see a little bump, a little hill that shows that it's crossing over, but many designers don't bother to use this tool. Instead, it's accepted practice to use solder dots as solder joins, and simple crosses are, we assume, they're insulated wires crossing over each other in 3D space. We've talked about the symbols before. Here they are again. You're responsible for all of these, and we'll probably play with almost all of these in our build phases over the coming months. We will highlight a couple of these just in terms of how best to display these and how to interpret these. So the power supply, of course, is the source of electrical potential. And in our class, we will stick to direct current, or DC. And if you see a single cell on that then battery, 1.5 volts is implied, but almost always you'll see the voltage written beside the battery symbol in the schematic. The larger bar represents the positive terminal of the battery, so we can see it at the top here. And a few more notes about the labeling. In our schematics, then, we're going to use the symbol for the battery, but when you're interpreting schematics you might pull from the internet or out of a book, you may see the power source written as VCC. It just may be labeled positive voltage. Sometimes we'll talk about it as being hot. It's almost always shown as a red wire in the actual design, and once in a while you will see a red wire in a schematic to represent that power source, that potential source. And one more thing, in general, circuits have the power at the top. That is, current flows downward. Keep this in mind and try to use this in your schematics that you draw as well. So you can see that this schematic that I've shown multiple times uses a lot of these approaches all at once. So we've got 9 volts labeled here. We've got a multi-cell battery. Positive is at the top because of the large bar. And I showed a red wire at the same time. Okay, the ground. The ground is a source of electrons. By convention, it's 0 volts. It's also thought of as the negative terminal on the battery, the smaller pole of the battery symbol, and we'll sometimes see it as this representation of a wire going into the earth. So our default circuit then here could also have been drawn. Instead of showing the complete circuit, at times we'll simply show ground symbol for the negative lead, particularly if it's a very large schematic and we don't have the room to make the wires go all the way across the schematic. So the wires themselves are likely to be connected up to the negative terminal, but we'll show it as simply ground. So these two diagrams are entirely equivalent. These are both circuits, and they're both the same circuit, could be wired up identically. And of course, if the positive is at the top of the circuit, by convention, usually the ground is shown at the bottom of the circuit in the schematic. Wires. Of course, lines represent wires, as we mentioned before. Schematics generally have the wires drawn vertically and horizontally. Okay, so this follows normal conventions. We see 90-degree turns. We see straight lines drawn horizontally and vertically. In general, this schematic, while really in many ways no different from the other one, is not following accepted practices because the wires aren't vertical and horizontal. So don't do that if you can help it. Current flow. We've already talked about the direction of current flow. It's from positive to negative, or from source to ground, if we want to say it that way, from hot to ground. In any simple circuit, the current flow is the same across any point. So when I say simple circuit, I mean any series circuit. The current's the same anywhere in the circuit if you measure it. And we won't talk too much about this because it's not that significant for our purposes from a practical point of view, but the direction of current flow, of course, is the opposite of the direction of electron flow. And so if we look at our default schematic, then the direction of current flow is shown as follows. Notice one handy thing. Our diode, now this is a light emitting diode, but it's still a diode. always points in the direction of current flow. If it doesn't, it's wired backwards. Okay, if you want to maximize your marks on tests and other submissions, you want to match the symbols clearly so that there's no ambiguity, there's no confusion about which symbol you meant. You want to be as tidy as possible. Remember, it's a communication device. And use a straight edge for wires. So you can use your calculator, you can use a ruler, but use a straight edge for wires on all submissions. And there are marks anytime you submit a schematic. There are marks for neatness and marks for accuracy. You might ask, are all these conventions requirements? Is the schematic wrong if it breaks the rules? No, absolutely not. They're guidelines, and any simple circuit you're expected to follow them. And they're extremely useful because engineers can look at a schematic that's drawn according to convention and envision the invention simply and easily, quickly interpret it. There may be times when you break some of those rules where you've got a curved wire, for example, or you have the power at the bottom instead of the top. But when you do this, you run the risk of people misinterpreting, and certainly you're going to make it slower for people to interpret your circuits. So if there isn't a significant reason to break from those conventions, just follow the guidelines that we've seen here. Okay, for your homework then, please complete the schematic worksheet. And if you complete that early, feel free to go ahead and look at the additional handout on using circuit drawing software. In your submissions, you may decide you want to use software to create very, very good circuits. There are some very good tools online to do this. Okay, thanks very much, and have a great day.